Earth is one of the most balanced worlds we know, a system carefully tuned through deep time. Every ocean current, every atmospheric shift, every geological process works together in a delicate equilibrium built over billions of years. But what if that balance didn't just shift? What if it collapsed? What if the planet crossed a point of no return and froze itself entirely? This isn't science fiction. This is the story of the day Earth became a giant ice ball. Welcome to the Snowball Earth event. During the Cryogenian period, something extraordinary and terrifying happened in Earth system evolution. The planet didn't just cool down gradually like a typical ice age. It plunged into a state of global glaciation where ice expanded relentlessly until it wrapped around the entire planet. Ice sheets didn't stop at the poles. They marched toward the equator. Oceans froze over. Continents vanished beneath kilometers of ice. Even regions that once hosted warm, tropical seas transformed into vast, silent equatorial ice zones. From space, Earth would have looked less like a blue planet and more like a white frozen sphere. A true planetary shutdown. This is what scientists call the Snowball Earth hypothesis. But how does something this extreme even happen? How does an entire planet lose control of its own climate system? The answer lies in one of the most powerful feedback mechanisms in nature, the ice albedo feedback, also known as the ice albedo effect. Here's how the mechanic works. Ice reflects sunlight. Water absorbs it. So as ice expands, more sunlight gets reflected back into space. That means less heat stays on Earth. Less heat means more cooling, and more cooling creates even more ice. It's not linear, it's exponential. A runaway chain reaction. Once Earth crossed a critical climate threshold, the system stopped stabilizing itself and started amplifying the freeze. Scientists believe this tipping point may have been triggered during the breakup of the supercontinent Rodinia. As continents shifted, rainfall patterns changed. This accelerated silicate weathering, a process that removes carbon dioxide from the atmosphere. And that's where things got dangerous. Carbon dioxide is a key driver of the greenhouse effect. When CO2 levels drop, Earth loses its ability to retain heat. So with increased weathering pulling CO2 out of the air, the planet's natural heating system weakened. At the same time, tectonic changes along mid-ocean ridges altered ocean circulation and heat distribution. The balance tipped further, and then the freeze began. The first major global lockdown of the planet's climate system was the Sturtian glaciation, a massive, prolonged ice age that may have lasted over 50 million years. And just when the planet began to recover, it happened again, even more intense, the Marinoan glaciation. These weren't seasonal events. They weren't even typical geological episodes. They were full-scale planetary transformations. At this point, Earth had effectively become a frozen system locked in stasis. Oceans were sealed beneath thick ice layers. Ocean circulation slowed dramatically. The water beneath became denser, increasing cold ocean viscosity, making movement even harder. The delivery of life-sustaining elements stalled. Nutrient diffusion dropped to near zero. Sunlight barely penetrated the surface, cutting off most photosynthesis. Surface ecosystems collapsed. From the outside, it looked like the end, a lifeless, frozen world drifting through space. Game over. But here's where the story takes a turn. Because beneath that ice, life didn't disappear. It adapted. In the darkest, most extreme corners of the planet, near hydrothermal vents, within hidden subglacial lakes, and in isolated meltwater pools, life found ways to survive. Primitive organisms, especially cyanobacteria, continued to function in limited conditions. These microbes sustained slow oxygen production, quietly reshaping the chemistry of the oceans. Meanwhile, deeper in the system, microscopic life, prokaryotes and early eukaryotes, relied on internal biochemical machinery like ATP, energy transfer, and the electron transport chain to maintain cellular metabolism. This wasn't thriving. This was survival under maximum pressure, and pressure changes everything, because while life was barely holding on, something else was building in the background: heat. With the surface frozen, silicate weathering, the process that removes CO2, nearly stopped. But volcanoes didn't stop. Through continuous volcanic outgassing, carbon dioxide slowly began to accumulate in the atmosphere again, year after year, century after century, million years after million years, until the atmosphere became loaded with greenhouse gases. This led to massive carbon dioxide accumulation, and eventually, Earth crossed another tipping point, the deglaciation threshold. And when that happened, the frozen world didn't gently thaw, it snapped. A runaway greenhouse effect kicked in, triggering rapid post-glacial warming. Ice sheets collapsed, oceans melted, the planet transitioned from a frozen wasteland into an intense ultra-greenhouse climate in a relatively short geological time. What was once ice became ocean again, and what followed would change life forever. Because this wasn't just the end of a frozen Earth, it was the beginning of a new one. But life didn't quit. Instead, it adapted. Beneath the frozen surface of the Snowball Earth, survival didn't look like dominance, it looked like persistence. Microbial life, especially cyanobacteria, retreated into the only safe zones left on the planet. Deep beneath the ice, around hydrothermal vents, inside hidden subglacial lakes, and within scattered meltwater pools, life found narrow windows to continue. These were some of the harshest extreme environments Earth had ever seen. Limited light, low temperatures, scarce nutrients, and yet not lifeless. Wherever even a trace of sunlight could penetrate, these microbes continued photosynthesis, maintaining slow but steady oxygen production. Not enough to transform the planet overnight, but enough to keep the system alive. Meanwhile, in the dark oceans below, prokaryotes and early eukaryotes pushed forward through time. Their survival depended on internal biochemical systems, cellular metabolism, ATP, energy transfer, and complex pathways like the electron transport chain and cytochrome C oxidase. This wasn't evolution in comfort. This was evolution under maximum evolutionary pressure, and pressure drives innovation. Because when survival becomes difficult, natural selection becomes ruthless. Only the most adaptable systems persist. Only the most efficient pathways survive. And over millions of years, those small advantages begin to stack. But while life was holding on, something else was quietly building. Not life, heat. With the planet locked in ice, silicate weathering, the process that normally removes carbon dioxide from the atmosphere, nearly shut down. But Earth's interior didn't stop. Through continuous volcanic outgassing, carbon dioxide kept leaking into the atmosphere, slowly, relentlessly, unstoppably. This led to massive carbon dioxide accumulation. The atmosphere thickened with greenhouse gases, restoring and then amplifying the greenhouse effect. Over time, the planet approached a critical tipping point, the deglaciation threshold, and when it finally crossed it, the change wasn't gradual, it was catastrophic. The ice didn't slowly retreat, it collapsed. A runaway greenhouse effect triggered intense post-glacial warming, flipping Earth from a frozen world into an ultra-greenhouse climate in a geologically short time. Kilometers of ice melted, oceans surged, massive sea level rise reshaped continents, and the planet entered one of the most dramatic transitions in its history. The geological record preserves this moment in stunning detail. Layers of cap carbonates were rapidly deposited over ancient glacial sediments, forming distinct markers found across the globe, from the Flinders Ranges to the Namibia glacial deposits, and as far north as Svalbard and Greenland. But the most important changes weren't on land, they were in the oceans. As glaciers melted, they unleashed a global nutrient pulse. Suddenly, oceans were flooded with essential elements: phosphorus enrichment, increased copper availability, and shifts in ocean alkalinity. This triggered a massive surge in marine productivity. The chemistry of the planet shifted rapidly. The carbon cycle was disrupted, leading to dramatic carbon isotope excursions and shifts in strontium isotope ratios. At the same time, rising levels of dissolved iron and oxygen fueled widespread ocean oxygenation. For the first time in Earth's history, conditions were finally right for complexity. Before this, life had been simple, dominated by microbial mats and layered structures like stromatolites, stable, efficient, but limited. Now, everything changed. The post-Snowball world created the perfect conditions for multicellular life evolution. Organisms began experimenting with multicellularity, developing cellular cooperation and increasing biological complexity. Cells specialized, systems formed. New biochemical demands drove innovation, from efficient protein enzymes to structural components like early collagen formation. And at the center of this transformation, the rise of mitochondria, enabling powerful energy production systems that would support larger, more complex life. This marked the beginning of the Ediacaran period, and with it came the first large complex organisms, the Ediacaran biota. Strange, soft-bodied life forms unlike anything alive today. Creatures like Dickinsonia and Kimberella, preserved as soft-bodied fossils and trace fossils in locations like Mistaken Point and the White Sea. These weren't just organisms, they were experiments, early attempts at early animal life. Some of these lineages vanished, part of ancient mass extinction events. Others laid the groundwork for what came next, because not long after, the planet witnessed one of the most important turning points in the history of life, the Cambrian explosion. A rapid diversification of organisms, the emergence of complex ecosystems, the appearance of body plans that still exist today, the foundation of modern life, and all of it, traced back to a frozen world. The Snowball Earth wasn't just a climate catastrophe, it was a catalyst, a complete system reset that reshaped biogeochemical cycles, intensified evolutionary pressure, and unlocked the origin of complex life. It proved something fundamental about our planet. That even under the most extreme Earth's climate extremes, life finds a way. That planetary transformation doesn't destroy evolution, it accelerates it, and that the path to complexity sometimes begins in ice. If you look at Earth today, it's easy to see stability, blue oceans, green continents, a system that feels permanent. But beneath that calm surface lies a history shaped by chaos, resilience, and survival in extreme conditions. A deep time perspective where even a frozen planet can become the birthplace of everything that comes after. And in that sense, the day Earth became a giant ice ball was the day the future began. If you found this story fascinating, do us a favor, like the video, subscribe to the channel, and stay connected for more deep dives into the hidden history of our planet.